So today we'll, since you're probably, I should have some commercial. This is your brain on an exam. You know, the one about, this is your brain on drugs. They have a frying egg. So I'll stop early today, maybe 10:30 or so, to give you a longer weekend. Okay. So we were, I want to revisit the moment generating function a little bit. This is the, oops, I'm sorry. No I here. And the important thing to remember about moment generating functions is if this converges for t in an interval about 0, then this completely determines the distribution of x. In other words, you can't have two different densities giving the same moment generating function. So you can use this, as I said last time, to determine probability distributions. So let's suppose that, did we compute this for Poisson? I forget if we computed the moment generating function for a Poisson random variable. You don't think so?
No, we didn't.
Okay, let's do x Poisson. Bless you. Okay, there's the PMF for the Poisson. Let's compute the moment generating function for it. Here we evaluate this function at k. And then we multiply by p of k, but I'll just write immediately here. Lambda to the k over k factorial e to the minus lambda. I'm going to factor out the term e to the minus lambda because it doesn't depend on k. Every term has that. And now here I have two things that are raised to the power k, e to the t and lambda. I'm going to combine those. And we come up with that. And now we stare at that for a moment, and a light comes on. I see it coming on here and there. You recognize it, and what is that sum? E to this. And we can combine these and write it as e to the lambda times e to the t minus 1. So there's the moment generating function for Poisson. If you see this moment generating function coming up as the moment generating function for some random variable, that random variable has to be Poisson with parameter lambda. Okay? Remember, I use this symbol. And then if y is Poisson with parameter mu, e to the t, y would be e to the mu, e to the t minus 1, right? And we'll use the notation capital M sub capital Y of t and read this. is the moment generating function of y at t. And here's the moment generating function for x. Sometimes we drop the subscript here if it's clear we're only working with one. I'm going to start working with a couple. Now suppose x and y are independent random variables. Last time we mentioned this. What's the moment generating function for the sum of independent random variables? Well, just by definition, the moment generating function of the sum would be you take the expected value of e to the t of the sum, e to the t times the sum. Now, exponentials factor like this. And here we have a function of a random variable, another function of a random variable, and these two random variables are independent, so the expected value of the product is the product of the expected values. Okay? So we've just shown that when the random variables are independent, the moment generating function for the sum is a product of the moment generating functions. Okay, well, let's apply this to an example. What would be a good example to apply this to? What pair of random variables would you like to try? No particular choices? I know. How about Poisson? Let's try it. We have them right here, right? So if x and y are independent, Poisson with parameter lambda, Poisson with parameter mu, respectively, then what do we get here? Well, for x, we get e to the lambda times e to the t minus 1. For y, we get e to the mu times e to the t minus 1. There it is. But if you have e to something times e to something else, you should probably combine that into 1e. And how would that combine? Okay, so what's the distribution of x plus y? Poisson with parameter lambda plus mu. In the test, this is a test problem, you probably didn't use moment generating functions. You can do it directly. There's a little step in there where you have to put in another term, but maybe you look back to your notes if you want. We did that in class by the old methods. But you can see this method is very easy then for determining distribution of sums of independent random variables. If x is normal with mean mu and variance sigma squared, then the moment generating function is that. We did that computation Wednesday. if xi is Bernoulli with probability of being 1 equal to p, and probability of being 0 equal 1 minus p, then the moment varying function was this. Can you do that calculation in your mind? X has only two values, 0 and 1. This one corresponds to the 1, right? When you get e to the 1 times t, and then probability being 1. Why isn't there a t here? Right, it's e to the 0 times t times the probability being 0. Okay. Now let's suppose x1 through xn are independent Bernoullis. What's the expected value of x1 if it's Bernoulli? Of just x1, not e to the t x1, just expected value of x1. Well, what values can it have? 1 or 0? The value probably it's 1 with probability p. So you get 1 times p plus 0 times 1 minus p, or p. Okay. What's the variance of x1? Remember what the variance is? How far you are from the expected value. It's squared. What values can this have? This is a random variable here, just kind of a little more complicated than that one. This could be 1 minus p squared or p squared, right? It's 1 minus p squared with probability. It's 1 minus p squared when x1 is 1, and that happens with probability p. So I get 1 minus p squared with probability p, and it's when I put 0 in here, I get p squared. It's p squared with probability 1 minus p. I can factor out a p and a 1 minus p from here. And what would be left here when I factor this out? One more power of this, right? So 1 minus p. What would be left here? P. What happens if I add 1 minus p to p? You get 1, so it's this. That's the variance. So I'm going to define new random variables, yi equal to xi minus p divided by square root p times 1 minus p. What's the expected value of yi? Well, it's expected value of yi over square root p 1 minus p minus, what would be the expected value of p over square root 1 minus p? Those are fixed numbers. What do you expect 2 to be? 2. What do you expect p over root 1 minus p to be? P over root 1 minus p. It's not random, so its expected value is the value. And here's a constant times a random variable. When you're taking expected values, that behaves like taking integrals. If you take an integral of a constant times a function, what do you do with the constant? Pull it outside of the integral, right?
Is that supposed to be yi there? Is that
Oh, thank you. Xi. Yes, Xi. Yeah, thanks. So, so I pull that constant out. Now the expected value of this is P. And you can see these two cancel. So all I did here is this. If expected value of x is equal to mu, then expected value of x minus mu is equal to 0. If you integrate a function and get a number, and then you subtract that number from the function and then integrate, you're going to get 0. And similarly, I won't go through this. The variance of yi is 1. Here's what we did. The variance of a random variable is sigma squared, then the variance of x over sigma is 1. Okay. Let's see if we can figure out the moment generating function for, yeah, question.
For this one, how come it's not 1 over root p times 1 minus p?
Oh, there's a misprint. There's a missing p here. Yeah, thanks. Do expected value of e to the t times yi. In other words, we're computing moment generating function for y sub I. It'd be that. And now I think that is equal to this because I break this exponential up into e to the t times xi over this, and then e to the t times e to the t times minus p over this. The second part that I just mentioned is a constant. It's not random, so I pull it out of the expectation. Okay. And so I have to do that. That's the moment generating function of xi at this value. And I think I did that somewhere. Well, I erased it. No, here it is. I need to write down the moment generating function for xi at this. So that means I should put what here? T over this, right? Okay. Now let's put this back inside. Okay. And now I'd like to take p equal to half for simplicity. Let's take p equal to half. So that'd be like fair coin. Well, what do we get? This becomes a half. What does this become here? 1 minus a half is a half. So the numerator here is a half. What do we have in the denominator? A half times a half is a fourth. Square root of a fourth is a half. So here we get a half over a half, or 1. So we just get t. Here we get a half. Oh, so I'm sorry, this is minus a half. No, that's a half. That's a half. And here we get what? E to the negative t. So 1/2 e to the t plus 1/2 e to the minus t. Or a hyperbolic cosine of t. Okay, cool, huh? All right. Now, what if we do this? We add up the y's and divide by square root of n. These are okay, I just wrote down the definition. I just put the root n under the t. Now let's use the fact that these are independent. So the expected value you see there would be the product of the expected values as follows. And they're all the same because they all have the same distribution. So this would be the same as the first one raised to the nth power. And what is this one before we raise it to the nth power? Well, it's a hyperbolic cosine at t over root n. And then we raise that to the nth power. And what is this thing inside doing as n goes to infinity? Before we do that, what does that do as n goes to infinity? It goes to hyperbolic cosine of 0, right? T over root n goes to 0. Hyperbolic cosine of 0 is 1. And 1 to the n is 1, right? Not so fast. This number, you have to worry about the relative rate, right? Depends on the rate. Do you remember how to do these indeterminate forms? Like if you have a ratio f of n, f of x over g of x, they're both going to 0, or they're both going to infinity. How do you determine the limit of the ratio? L'Hopital's rule. Maybe we could try to guess. What does this look like for small values of t, or t over root n? What's the Taylor expansion for e to the t? If t is really small, which terms really matter here? Only the first couple, right? Higher powers are less. E to the minus t would be what? Okay. And what happens when we add these two together? What do we get? And divide by 2. We get 1 plus t squared over 2, right? And then plus other stuff that's not as important. So what does hyperbolic cosine of t over root n look like for n large? Only the first couple of terms will matter here. We get a 1 plus, now we replace this by t over root n. What do you get? T squared over 2n. Okay? So let's put that inside for the hyperbolic cosine. The other terms won't matter. And do you know what that does as n goes to infinity? Nope. This is one of the most fundamental limits in calculus. There are two very important ones. Limit x goes to 0 sine x over x. That one's 1. This one, do you remember that from calculus? You can figure this out by taking log of that and then using L'Hopital's rule. And the log of this goes to x. Okay. So what does this do as n goes to infinity? Converges to e to the t squared over 2. So the moment generating function of this thing, or I guess this thing, converges to this. Is this a moment generating function of anything? Well, usually I leave these things on the board when I ask a question like that. I hit the normal with mean 0 and variance 1. So that's called the central limit theorem. That the distribution of y1 plus dot 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 plus yn over square root of n is approximately normal, mean 0, variance 1. Okay, so if you start with Bernoulli's and you normalize by subtracting the mean and dividing by the variance, square root of the variance, and then add up independent ones, divide by the square root of the number of summands, that's almost a normal random variable with mean 0 and variance 1. Okay. In the book, it tells you why these things are called moment generating functions, because if you differentiate once and evaluate at 0, you get the expected value of the random variable. If you differentiate twice and evaluate at 0, you get the expected value of the square. What's maybe even more interesting is to take the log of the moment generating function and differentiate that twice. Let's differentiate this twice. And then we're going to evaluate it at t equal to 0 afterwards. We differentiate the log of some function. How do you do that? You get the derivative of the function over the function. Okay, that's what we get when we do one derivative, then we have to differentiate again. Okay? Now what's the derivative of this? This means derivative with respect to t. Let's differentiate under the expected value. Derivative of e to the tx would be x e to the tx. So from here to here, we just did this differentiation. Okay? Now we have a quotient. We have to apply the quotient rule to differentiate. When we differentiate the numerator, what happens when we differentiate this? We differentiate under the expected value sign. What happens when you differentiate that with respect to t? Well, this doesn't change. This is a constant as far as t is concerned. We differentiate that with respect to t, and x comes down. So we'll get an x squared e to the t capital X. And then we have to multiply by the denominator. And then we subtract the derivative of the we subtract the numerator times the derivative of the denominator. What's the derivative of the denominator? Well, we just did it. It's this. So we get another factor of this. We have to multiply by this again, so that thing's squared, right? And then we divide by the denominator squared. Okay? Now let's evaluate at t equal to 0. And what do we get? Here we get the expected value of x squared. What do we get here? When t is 0, e to the 0 is 1. Expected value of 1 is 1. What do we get here? This becomes 1 times x. We get expected value of x, quantity squared, from here. And what do we get in the denominator? 1. So we get this. And what is this?
Variance.
That's the variance of x. So So if you want to compute the variance of a random variable, compute its moment generating function, take its log, differentiate twice, evaluate at 0. Okay, well, let's do it with this. Just for it's here, so let's do this one. Okay, so what do? Here's the log of the moment generating function. You differentiate it twice. What do you get when you differentiate that twice? First time you get mu and then sigma squared t, right? Second time you get sigma squared. What's the value of that when t is 0? Sigma squared. So the variance of a normal is sigma squared. Okay. Let's do it with Poisson. What's the variance of a Poisson random variable? There's the moment generating function for Poisson, right? What's the log of that? There it is. If I differentiate twice with respect to t, I just get lambda e to the t. Means the variance of Poisson is lambda, because I evaluate this at t equals 0, I get lambda. If you do this calculation using the PMF of the Poisson, you can do it. But it has several steps. This is much easier. What if x is binomial with parameter n and p? Let's calculate the variance of that. Well, we know the expected value of a binomial with parameters n and p is n times p. How do we know that? Well, we did it before, I think. Or perhaps it might be easier to do this. The variance is also this, and that would be the sum k equals 0 to n k squared, n choose k, p to the k, 1 minus p to the n minus k. And then we know this is np, so it'd be minus the quantity n times p squared. And then we'd have to do several manipulations involving cancellations of the k squared with the stuff that comes from the binomial coefficient and try to rearrange so that you could recognize it and put it all back together again. So that would be how you do it directly. Or we could use the log of the moment generating function for binomial. What is that? So with the same x, okay, can we evaluate that? Well, you probably want to get this e to the t together with that p, because they're both raised to the power k. So they look like they're made for each other. Yeah. Whoa, yeah, I went too far, didn't I? But actually, it didn't matter, because this would tell me what when k is bigger than n. Let's n choose k if k is bigger than n. How many ways can you choose n plus 1 objects from a set of n objects?
No way.
There's no way to do that, right? So even though I made a mistake, it was covered up by this guy. He saved me. But thank you. That's correct. And does this admit of any simplification?
P to the t plus 1 minus p raised to the x.
Right. Binomial theorem says that this is p e to the t plus 1 minus p raised to the n power. And what's this thing inside? Before I raise it to the n, what's that? That's a moment-generating function for a Bernoulli with parameter p. And what moment-generating function would this be if I raise it to the nth power? That's a moment-generating function for the sum of n independent Bernoullis with parameter p. So what does it say about the binomial and the sum of n independent Bernoullis? They're the same. A binomial random variable with parameters n and p has the same distribution as the sum of n independent Bernoullis with parameter p. This is the moment-generating function for n independent Bernoullis, sum of n independent Bernoullis with parameter p. And it's also the moment-generating function for a binomial with parameter n and p. By uniqueness of the moment-generating function, we see the two distributions are the same. Okay? So what was our quest? We wanted to compute the variance for the binomial. And how do you do that? Well, okay. So here's our moment-generating function. We should take its log. And then we're going to evaluate it at t equals 0. So I'm going to, in order that I don't have to write this every time, I'm just going to say log. Okay. And the first time I differentiate, this n I'm going to put outside always. I differentiate this with respect to t, right? And that gives me p e to the t over p e to the t plus 1 minus p. That's from the first differentiation. And now I differentiate again. And then in the numerator, I get p e to the t when I differentiate that. And then I have to multiply by the denominator. And then I take the numerator minus the numerator times the derivative of the denominator. But the derivative of the denominator is p e to the t, so I get this thing squared. And then I divide by the denominator squared. Okay, and now I evaluate it at t equal to 0. I just put t equals 0 in here. Well, there's an n out in front. So all the e to the t's will become 1. E to the 0 is 1. So I get p. What do we get here? One minus p squared over 1 squared. Or n p times 1 minus p. That's the variance of a binomial. Much easier calculation than this one. Okay. Any questions? Does anybody think the moment generating function is useful? Yes. Okay. All right. Change gears slightly. Suppose we have a pair of jointly distributed random variables. And they both have finite expected values squared. The square of the random variables has finite expected values. Then the covariance of x and y is this thing. That's the definition of covariance. Before we compute, let me just ask if x and y are independent. What is their covariance? Well, here we have a random variable, x minus its expected value. Here we have another one, y minus its expected value. They're independent. We're taking an expected value of their product. That would be the product of the expected values. What's the expected value of this? When we subtract the expected value from a random variable, take the expected value, you get 0. So the answer here is 0. Okay. Suppose we have a bunch of random variables that have finite second moments. Let's compute the variance of the sum. Get that? Right? The variance of a random variable is that random variable minus its mean, and you square the difference, and then you take expected values. And I'm going to combine those sums. Like that. Now if I have a sum of numbers, I equal 1 to n, a sub I, and I square it, that's the sum I equal 1 to n of a sub I times the sum j equal 1 to n a sub j. And then what do I have to do? This is the sum I and j going from 1 to n ai times aj. And I like the diagonal terms, that is where I and j are equal. That would give me the sum I equal 1 to n ai squared. And then I get the sum where I and j are different, ai, aj. But this is symmetric, where an I is bigger than j and j is less than I can express this as a sum I equal 1 to n ai squared plus twice the sum over I less than j, ai, aj. Okay, so I'm going to do that here. These are the AIs. Here's the AI squared. Here is the AIAJ term. AI squared, AIAJ. And now I can take the expected value inside the sum. Like that. Okay. Now, what is this term? I have a random variable. I've subtracted its mean. I squared it. I took the expected value. That's the variance of xi. So this is the sum of the variances. What's this term? I have one random variable. I subtracted its mean. I have another. I subtracted its mean. I multiplied them together and took the expected value. That's the covariance. Of xi and xj. So what do we get? The variance of a sum of random variables is the sum of the variances plus twice the sum, and maybe I'll refine the limits here a little bit. 1 less than or equal to I less than j less than or equal to n. Covariance of xi xj. Okay. What if the random variables are independent? What would the variance of the sum be? If x1 through xn are independent, what would happen to the right-hand side? Well, that wouldn't change this. What would that be? That would be 0. So if x1 through xn are independent, the variance of the sum is the sum of the variances. We can't take variances if the expected value of xi squared are infinite. Okay, so now, what's the variance of a binomial with parameter n and p? Well, we did compute it, and I erased it, but it's np times 1 minus p. We did that with the log of the moment generating function, differentiating twice, evaluating at 0. Here's another way to compute the variance of a binomial with parameters n and p. What's a binomial parameter n and p equivalent to? It's equivalent to the sum of n independent Bernoullis with parameter p. The binomial with parameter n and p has the same distribution as the sum of n independent Bernoullis. Why do we know that? The moment generating functions are the same. So if we have n independent Bernoullis, the variance of their sum would be the sum of their variances, or up here. But what's the variance of a Bernoulli? Remember, the expected value of a Bernoulli is p. The variance of a Bernoulli would be expected value of x squared minus the expected value of x, then you square after taking expected value. What's the expected value of x squared? X is Bernoulli. What values does a Bernoulli take on? 0 and 1. So what values does x squared take on? With the same probabilities that x does, right? So this is the same as the expected value of x. What's the expected value of x? P. So the variance of a Bernoulli is p times 1 minus p. What would be the variance of a sum of n independent Bernoullis?
Sum of variances.
And that, how many do you add up? N of them. So n p 1 minus p. Okay. Let's try one more example. If x is normal with mean mu and variance sigma 1 squared, and y is normal with mean nu and variance sigma 2 squared, then they are independent. What is the variance of the sum? It would be the sum of the variances. What's the variance of x? Sigma 1 squared. What's the variance of y? Sigma 2 squared. So the answer is sigma 1 squared plus sigma 2 squared. Okay. So I ran over 5 minutes. We'll stop here.